In the world of machine learning, building the perfect model is really about achieving a single goal. Instead, every decision involves navigating a landscape of compromises, or trade-offs. Today, we'll explore some fundamental trade-offs that shape how effective models are designed and deployed in the real world. Let's start with the classic, the bias-variance trade-off. Imagine you have data points you want to model. Bias refers to the assumptions a model makes. High bias models are too simple and underfit the data. They fail to capture the underlying patterns, like trying to fit a straight line through a curvy trend. Variance, on the other hand, measures how much the model's prediction changes with different training data. High variance models are too complex and overfit the data. They essentially memorize the noise and fluctuations in a training set, performing poorly on new, unseen data. The goal is to find a balance, a model complexity that is just right. This model captures the true underlying pattern without being overly sensitive to the noise. This sweet spot minimizes the overall error on unseen data, which is what we truly care about. Next, consider the trade-off between model accuracy and the time it takes to train the model. Generally, more complex models can achieve higher accuracy, but they demand significantly more computational resources and training time. Let's visualize this. A simple model, like linear regression, might train very quickly, but might have moderate accuracy on complex data. A complex model, like a deep neural network, might take much longer to train, but can potentially achieve much higher accuracy. The choice depends on the application. For a real-time mobile app, speed is crucial, perhaps accepting slightly lower accuracy. For medical diagnosis, maximum accuracy might be paramount, even if training takes a long time. For classification problems, precision and recall are often inversely related. Imagine we're classifying objects as positive or negative. Precision answers. Of all the instances the model predicted as positive, how many were actually positive? High precision means fewer false positives. Recall answers. Of all the instances that were actually positive, how many did the model correctly identify? High recall means fewer false negatives. Another increasingly important trade-off is between data privacy and model performance. Techniques that enhance privacy, like differential privacy or federated learning, can sometimes lead to a slight decrease in model accuracy compared to training on centralized, unprotected data. Successfully applying machine learning means understanding and carefully managing these trade-offs. The optimal balance is always dictated by the specific requirements, constraints, and goals of your project. By carefully evaluating what matters most in your context, you can build machine learning solutions that are not just accurate, but also practical, efficient, and responsible. Thank you for watching.